I'm going to talk about cryptographic hash functions. And before everything, I just want to introduce two characters. This is an honest person, and this is a dishonest person who's an attacker. So let's start with an example scenario where Alice has a will, and she wants it to be protected so that after her death, so this will is properly given to her heirs. So this is where she doesn't need the will to be secret, but she needs the will to be satisfying this property called integrity, where the will cannot be changed. So for achieving this property, what Alice can do is that Alice can take a will and then sign it here. So, so that after Alice dies, Eve cannot forge this because Eve cannot forge the signature of Alice. So the electronic equivalent of this document and fingerprint is message and digest. So what happens is that there is a message which is passed through a hash function and then compressed to get a message digest. This is unique for that message, and it's a compressed version of this message. So this is equivalent to the fingerprint concept. So this is how, if a message is tampered, so what can be done is that later, so the message and the message digest both can be sent, and if the message is tampered, the message digest, like if this is tampered, the message digest will, this will yield a different message digest. So they can identify whether the message is integrity, message is not tampered or tampered. So this is how they can check the integrity. So this is a, here it is. So cryptographic hash functions can be used for checking integrity, and there are various other implementation scenarios like authentication, and then digital signatures, and there are digital timestamping, and many others. Timestamping. So these are the few applications of hash functions. So now I'll start with the definitions and so this is a function. So it maps function. It takes a message of size, no specific size, and then it maps to this digest, which is of size n, and n can be greater or equals to 1. So this is the definition of hash functions, and then hash functions can be of two types: keyed hash functions and unkeyed hash functions. So this is generally the message authentication code that we always refer to, and unkeyed is message detection code, manipulation detection code, sorry. So this can be one-way, two types, one-way hash functions, and then collision-resistant hash functions. So for our talk, I'll be talking about this unkeyed hash functions, this one-way properties and this collision resistance properties, and few construction on number theory approach for these kind of hash functions. So one-way hash functions. First property should be, this hash function should be publicly available. Publicly known, as in it should not be secret, the construction of the hash function. And then this hash function can be applied to messages of any length, as I have mentioned here. So in actual, this length can be bounded by some huge constant, which is larger than any size that we will ever want to hash. And then, given this hash function and some message m, h of m should be easy to construct, easy to calculate. Given the hash function, given this thing, digest, this is the digest, message digest, it is difficult to invert this, as in get a message m such that, m dash such that h of m equal to h of m dash. So we know about this hash function and we know about this digest. So it is difficult to invert. So yeah, this property is called pre-image resistance. This is the next property is that given the hash function, given the message, and given the hash of the message, it is very difficult to find another message m dashed such that h of m equal to h of m dashed. So these two properties are a bit different. Here the message is not given, it's just inverting it, and this is called the second pre-image resistance. And then this is another property. There are no other properties. So this is definition of a one-way hash function. And now we talk about collision resistant collision resistant hash function. Here, all these previous properties should be satisfied, and on the top of that, we have to find two messages m and m dashed from the scratch such that h of m equal to h of m dashed. So this is one of the very important properties of hash functions, and all the hash functions are constructed keeping in mind the attacks that can be made into this property. So finding attacking this pre-image resistance property is relatively difficult than this, and also this is relatively difficult than this, but this is easier than these two attacks. So whenever we construct a hash function, like there are very famous hash functions like MD5, SHA1, SHA512. These are the practical hash functions. I won't be talking about this today, but these kind of hash functions are weaker because their message, because it is not safe from this collision resistance attack. So this is a very important property that we are going to talk about today. So
because there's another type of collision resistance, right? To find a random two message that give you the same.
Yeah, that's what I was talking. So like you have two messages m and m. You have to devise it from the scratch. Find two different messages such that they yield the same digest. So you are not given any one message.
There's
So
another
here
question.
you are given one message and then digest, and then you find another message
Oh, I
such
see.
that it's equivalent to this. But here you have to find them from the scratch.
Okay, I see.
So
That's how you did, right?
I'll just write this down once. So in this pre-meta talk, let's consider y equals h of x, h of m. So in this pre-meta talk, we are given y, and the attack is find m dashed such that this is the pre-image attack. The second pre-image attack just write it down once. Given y and m, dashed such that h of as in y equal and collision resistance should be given none, find m dashed such that h of m equal to h of m dashed. So these are the three attacks that we will be talking about today. Random oracle model. So a hash function, this is an ideal mathematical model. So a hash function, if you want to construct a cryptographic hash function based on this model, so then it should be having the following properties. So like when a new message of any length is given, the oracle creates a digest of which is a random series of zeros and ones and of specific number of bits, and then saves it in the oracle. And then the second property is that, and it saves the message. So if you give a message of this, it will just create something like this, and it saves it there. And then when a message, and it saves it there, yeah. So when a message is given for which the digest already exists, it just outputs that. And the third property is that the digest for a new message needs to be chosen independently from all the previous digests. So like, let's consider a scenario, like there is a table. Let's say our n will be of 16 bits. N is the size of the message digest. So we can input a message here, any message, and let's say there is a fair coin, and it will flip 16 times, and the corresponding 16 bits are saved here. So for another message, they might not be of the same length, but again it's flipped 16 times, and then it can be saved here. This is how it's like a table, and this is not made in an exhaustive manner, as in not all the values will be selected always, but there are chances where a value can get selected more than once. So this is a random oracle model, and this is a hash function based on random oracle model, and I am going to talk about attacks on this model. These are the generic attacks on this model. So the generic attacks, since this thing doesn't have a key here, so for a generic approach, we cannot do exhaustive brute forcing key. So what we can do is that we can, the generic attack on this model will be based on the size of the digests. So we have to make a hash function, whenever we are making a hash function, we have to make sure that this size is not that small, so that attacking this hash function is difficult. So, one more concept I want to say, that a hash function is collision resistant. A hash function is collision resistant if a polynomial time algorithm can find a collision. And it's very possible because this has infinite values. But this has finite values. This is the message digest. This is the message. So this has infinite values, but this has finite values. So finding a collision should be existing. And finding, this collision resistance property, if a function is collision resistant, it means that no polynomial time algorithm can find a collision here. But the point is that it's not that impossible. Because let's say there are two messages M and M dashed. And there is an algorithm which has hard-coded values of these two. Then it can find a collision in a constant time, right?
Sorry, is the R fixed, or how can you have infinitely many?
No, it's not R, it's a star.
Oh, the star.
This is star, sorry. This is star.
So still infinitely many potential issue? Or just finite?
No,
But just larger amount.
Well, star can be anything, right? It's not hash functions, it's just like arbitrary.
So finding a collision is not that difficult, because if an adversary, say this is an adversary, and it has these two values hard-coded, then finding a collision can be done in constant time. So
if they hash to the same, right? If they have the same hash, right?
Yeah.
Oh, that's what you're.
This is public.
Oh, yeah.
This hash function is always public. So this can be done in constant time. So, and if this is broken, then nothing can be done to get it back. I mean, this is broken forever. Right. So for considering, and we don't care when we are defining security, how to make this algorithm where these two values are hard-coded. Our only objective is, if there is such an algorithm, then it's broken. So what we do for defining for defining the security is consider a family of hash functions.
There is no star. It's any link.
So H belongs to.
No, it's not a bound. Any link template. The star is any.
That's really weird. Why? Because of twice that now.
Yeah, it's okay.
What's the question?
It's an algorithm that hashes a
You pick the message, so you know the link.
message of arbitrary length into a hash of finite length, or of a given length.
But you don't have a bound for the length.
No,
No.
You should have a bound.
Well, no, an algorithm doesn't need, like,
It's like saying
I mean, the message is finite, it's just that it doesn't matter what the length is.
it's like
The
saying
algorithm still works with it.
You can't have an algorithm that adds arbitrary size integers.
Or
You can
not.
only add integers
Oh,
up
it's
to
not the problem, it's
100.
just the algorithm. It's not
That's just the
problem.
input link. Any length input. It's just saying it's not unknown. It's just arbitrary.
Okay, I see.
Okay. Okay. So for defining security of hash function, what we can do. So this thing I already told you. So what we do is that we define this family of hash functions, and H belongs to this. H is this where H is a hash function of some definite n. N is the digest, length of message digest. So H is the family. It contains all the hash functions which has an output of length n. And this family has exponentially many hash functions. So now, even if an adversary knows what are all the hash functions contained in this family, but the polynomial time algorithm can find out a collision because the adversary doesn't know on which hash function is being challenged. So that is why I talked about this family of hash functions. I'm going to talk about two things. I guess everyone knows about this. So if there are n pigeon holes and n plus 1 pigeons, then at least one hole contains 2 pigeons, right? And the other thing is, if there are n, generalized principle is if there are n pigeon holes and kn plus 1 pigeons, then at least one hole contains k plus 1 pigeons. So why I'm talking about this is that the message digest size is small and the number of messages are large. So collisions are bound to happen. Another concept which I think everyone knows still. First problem.
So what does it say?
Huh?
Predefined value, okay.
Sorry. So, the thing is that there is a random variable distributed. There is a random variable with n possible values from 0 to n minus 1. So what is the minimum size of this number of messages here? Let's say there are k messages here. So what is the minimum size of k? What should be the minimum size of k such that one of the values should be identical to a predefined value with a probability greater than half. So this is the first problem. It is equivalent to this pre-image attack. So let's say hash size is n bits, and we have 0 to 2 to the power, let's say, okay? So these are the possible, this is the possible range of hashes. So this attack is like, what is the minimum size of the messages? How many messages should we consider such that if you remember the pre-image attack, we already have a digest Y, and we want to invert that. So point is, what is the minimum size of k such that it is equal to a predefined value with a probability greater than half? So this this is relevant to the first birthday problem, and it says that The minimum size of, I'm not going to deduce this, the minimum size of k should be something, so where n is the size of message digest. So this should be the minimum sample size, that is k should be proportional to 2 to the power n. This pre-image attack is not very, but quite difficult if the, this size is 512 bits or even 256 bits. Because 2 power 256 is for attacking this thing will take a lot of time. So
you don't
this
even have that many axles in the universe.
Huh?
You don't even have that many axles in the universe.
this is,
You can do it in 1 second.
second problem is that you already have a message, and this is, so if you remember this thing, you already have a message m and you have the h of m. So how likely it is that you find another message m dash such that the hashes are equal. So this is equivalent to the second problem, and it's also found out that it is equivalent to 2 power n. I'm interested in the third problem, so I am going to deduce the third one. So, should be the least size of k such that at least 2 messages are equal with p greater than half. So this is actually the collision resistance property. So I'm going to show the value k that is coming proportional to. So k is the size of sample messages as in, and n, as I said, number of digests, which is value of n is 2 power n. And let's say probability pi. Pi is the probability that sample I is equal to at least one of the previous values, previous samples. Samples as in messages here. Okay? So this is probability Pi. Qi is the sample I is not equal to any of the sample I is not equal to any of the previous samples. So if you see P1 will be 0 because before P1 there are no samples and Q1 is 1 minus P1, so 1. P2 should be 1 by n because there is only one sample before P2 and it should be one of the two n values. So like this, and then Pk should be k by n and Qk should be 1 minus k minus 1 by n, right? assuming all the samples are independent. So we want to find probability of Q, that all the samples are different. Okay, right. So it should be we use this approximation, okay, and so and then equivalent to the probability that at least two samples have the equal values, it should be 1 minus power minus k square by 2, right? So we want this to be, this probability should be greater than equals half. So if we reduce like this, it should so this should be the minimum size of the k, number of messages, which is proportional to n by 2. So this is the estimate of creating a hash function. So like we check like SHA F512 is quite secure because for attacking this, it will take 2 power 256 trials, which is quite time consuming. Now I'll just get back to the instructions. Iterated hash functions. The concept is that you have a big message M. So you divide it into blocks. Divide it into blocks of say m bits each. And then you also add a padding such that the, this is included in this, like the message is this, and then there is a padding. And then this is, after adding this, this is the second step where it's divided into t blocks of m bits each, and then this is the important part. There is a function. compression function. Just say f. Just draw this one. This function f is of n bits, is of n bits, output is of n bits, and this is done. So this is called the Merkle-Damgard construction. So there is a compression function. So our objective is that taking a message of arbitrary size and then compressing it to some fixed size. So how do we achieve that? We achieve that using iteration. So this is a function. It takes input of fixed size and produces output of fixed size. And we keep on iterating that till we get the desired output. So this is called Merkle-Damgard construction. So this value, h0, it can be a secret value as well. It should be a secret value. It's called the initialization vector, and then so if we need to construct this compression function f in a manner that this is collision resistant. If this is collision resistant, then the entire hash is collision resistant. So there are many approaches, like there are a few hash functions which are created from the scratch, and they are just added into this structure. So like there is a hash functions like MD5, SHA1. They are constructed in this manner. Even there are many hash functions based on block ciphers like DES. The actual thing is that you have to just add it here, and this should be collision resistant. So this is it. So I'll talk about hash functions based on molecular arithmetic. So the idea is to reduce the security of the system to the difficulty of some hard problem in number theory. So like there's a factorization problem. Given a composite number n. So this is an integer factorization problem. So if you are given that, finding this where p, q are distinct large primes. It is an open problem. And it's a very difficult problem, so one of the constructions take advantage of these factors. And there is this other problem, discrete logarithmic problem. Based on multiplicative cyclic groups. So like if G is a all the elements can be, and G is the generator of G, then so all the elements can be expressed like this, and problem is to minus this y plus G. Finding this is hard, so so the hardness depends on the choice of groups. For cryptographic purpose, we select this to be P, but we have to make sure that P minus 1 is not the product of,
Smooth.
yeah, so, yeah.
Can you reach the other side?
Mm-hmm.
Don't go.
It's fine.
Davies and Price proposed this thing. So this is a construction based on this. So there you see the R is the modulus where
Yeah, you can use the other.
so since factorizing this is a hard problem, so solving this is quite hard. I'm going to show how. So if this is solvable, then it has
X squared.
huh?
X squared.
Ah, sorry. Okay. So this is a quadratic residue modulo n, and P is an odd prime with P where P doesn't divide Y, then it should be either having 0 solution or exactly 2 solutions. So I'm going to show how. So let's say x0 is a solution. X0 is a solution. So minus x0 should be a solution. Because we want to show that if there is a solution, there are exactly two solutions. So if this is true, this should be true. Now we want to show that there are no other solutions. So let x1 be a solution such that so if both are the solutions, both will be true, then subtracting. Then you should be dividing this.
Yep.
So you can either divide so we get that. But we initially assumed that this is not true. So there is no x1. So if this has a solution, then it should be exactly two solutions and no more. The other thing I want to show is if Y is a quadratic residue, it should be satisfying this. And if we can find this property, then we can easily find out. I'll just show this. So one of these factors should be 0. if y is a quadratic residue, so it should be satisfying this property. So this quadratic residue problem is easy to solve with prime modulus. But the hash function we were talking about, it was this. This is the hardness of integer factorization problem, because we don't know what are the two primes, which is a product, n of which n is a product of. So since we don't know this, so it is very difficult to solve this. So I'll just show one thing. So let's say it can be factorized. So we get from here, we get So using CRT, we can, solve for this 2 power 2 values. There should be 4 equations, and using CRT we can solve this. So that is how this cannot be factorized. So this is a hard problem. But this hash function is not that secure. One of the reasons is that if I get a message X, and the second pre-image property is that if I get a message X and I know the hash of X, I can always know that there is another function, another message minus X, whose hash will be equal to this, because they are the same. So this is not resistant to the second pre-image attack.
Usually you have 3 minutes.
Mm-hmm.
You have 3 minutes.
What?
You have 3 minutes left.
Oh, I wish that. One more thing to say. Just. So another approach is like n is on RSA modulus. This is another hash function. So a compression function. H. H of x, G of x, mod n. So this is another hash function. So, like if someone can factorize n, then they can get phi of n, which is p minus 1, q minus 1. And now, equivalent to this value should be equivalent to this because this part will yield 1 according to this Euler's theorem. So x is not equivalent to x plus phi n, not equivalent to x plus k phi n, but still they all yield the same message digest. So if we don't know the value factorization of n, so it will be difficult to create collisions for this type of messages. And also this thing, the first pre-image, as in calculating, inversing this will be difficult because this is the hardness of discrete logarithmic problem. So this is a hash function which is both collision resistant, first pre-image resistant, and second pre-image resistant, because given one of the values of x, if like we get this, so it's hard to get another message which gives the same message digest, or even collision resistant, because creating two messages from the scratch, if we do not know the factorization of n, is difficult. So we can say that this is collision resistant as well as.
You can show the opposite, right? If you can find, like to show it's collision resistant, you can find 2x that gives the same answer. You can actually factor in. That proves it's collision resistant.
Yes. If you cannot factorize n.
I mean,
But you can
the opposite way.
You can do the opposite way. If you find two solutions like that, you can actually factor in.
So if you find like so x prime equals gx n, then you kind of get some g's and kr. Suppose r is the order of g, and then this is my n. And then
R is the order of g. Okay, cool.
yeah, you know
fine.
x as like something like this. N, right? And then you kind of have x squared. This is not my n.
Thank you, Shalini. We've got a meeting as well, but thank you. That's good.
Okay. And then you got this. So you got x squared minus 1, sorry, equals 1, minus 1 equals 0, 1 n. And then x plus 1, x minus 1 equals 0, 1 n. Okay, then I guess, so n divides the product of these two things, but,
Yeah.
but n will not divide any one of them,
Yeah.
right? And n, remember, n is just PQ, the product of two primes. And then the only possibility is that one of them divides one of them, and the other divides the other one. So suppose without generality, this is one. So P divides this guy, and Q divides this guy, right? And then we will get then we know that it's very clear that x plus 1, GCD, and n will give you P, right? And the GCD of x minus 1 is an n. Sorry, the n is the small input one. Will give you Q. So you kind of factor this down.
Right, so actually, if you find x and x prime, then basically you factor the n.
Any other questions?
Thank you, Shalini. Two things. Does anyone looking at U30 want to do a presentation next week or the week after?
Sorry.
We have this meeting right now.